Good morning, good afternoon, good evening. My name is Dan-Marius. I am from Romania, and I am from Gheorghe Saki Technical University of Iași, Faculty of Electronics, Telecommunication and Information Technology. In this presentation, I will show two practical applications based on the real-time NuttX operating system. Both applications were developed in the frame of the NXP Hover Game Challenge, a competition in which I participated in all 3 years of occurrence. A competition in which I took first place twice and second place once. The applications aim: the first one to detect people in the area with forest fire, and the second one is to detect and classify diseases in the vineyard. Both applications are based on an UAV system that was especially developed for each of them. As you know, NuttX is a scalable, small footprint, efficient, very stable and open source real-time operating system. And it is also, from my point of view, the base for running PX4 autopilot on a flight management board. I interacted with the NuttX operating system at many levels, as you will see in my presentation, and it is important to have a best understanding of it in order to achieve good results. One of the most disturbing problems in fire is the human death toll. As a direct result, one of the most significant challenges the rescue and search team face during a fire in the wilderness is the actual search for survivors and victims. So, this project aimed to develop a real-time UAV system capable of detecting humans in disastrous conditions like fires. The solution is based on an autonomous UAV that is able to both detect humans and send warnings promptly to a control center. The UAV system will carry a pre-programmed flight mission by following a planned path above the interesting zone, and at the end of the mission it will return to the landing point. These functions are embedded in the PX4 autopilot. The UAV system was built based on the Hover Game Drone Kit, which is a professional development kit produced by NXP Semiconductors. This kit contained all the required components needed to build a quadcopter, such as frame, motors, flight management unit or power distribution board. The human detection function was implemented using a Raspberry Pi as a companion computer. Also, an FPV system was used to check the detection made by the intelligence system independently. The Hover Game drone can fly autonomously, but based on a radio control link, a ground control operator can take control of the drone, switching from the autonomous mode to the manual mode. By using a telemetry connection, which is the main link with the ground station, it is possible to configure the flight path, supervise and change settings and parameters on the flight management unit, and in this mode to check the status of the Hover Game's quadcopter while it is in air, but most of all, the human detection from the Raspberry Pi are sent to the ground station based on this link. Communication between the flight management unit and the companion computer was done by using an I2C protocol. In the case of the human detection system, nothing is special or unusual. The HAR cascade provided by the OpenCV and a linear SVM classifier were used to perform human detection in the video streams. Of course, any other type of detection system can be used here. But there was a problem. In a real situation, human detection took between 2.4 and 2.9 seconds, and this detection time was unacceptable. To solve this problem, a multi-thread approach was employed, in which the 3 different recognition threads were running on the 3 distinct cores of the Raspberry Pi system in parallel. So, the main idea is to start this thread using a timer, but each thread was delayed by a third of the detection time. The detection speed improved in this mode, and in this mode I got around 1 frame per second. Right now, we have the detection, and you must send these results to the ground control station. To achieve this goal, a special app running on the NuttX operating system was developed as an independent module able to get the detection result through the I2C bus from the Raspberry Pi and communicate with the PX4 based on New York messaging. Based on these messages, the information was sent to the telemetry link to the ground control station. So, my app creates a background task based on this function, and this new background task runs independently from the parent. In the background task, I created and initialized several objects, such as a named semaphore and a timer. This was a point where I started to fall in love with the NuttX operating system. Due to compliance with the POSIX standard, all the interfaces for these components are identical to the one found in the Linux distributions. So, to develop this app, I first created and configured a timer. Based on this configuration, the kernel will send a signal each time the timer expires. In the second section, the timer expiration values are set and the timer is armed. In the last step, the signals and my functions association is made based on the SIG action system call. In this function, the human detection information is obtained through the I2C bus and sent to the PX4 autopilot based on the New York messages. Of course, in the end, the PX4 autopilot sends this information to the ground station based on the Mavlink protocol. In conclusion, it is very easy and straightforward to develop code in the NuttX operating system, and all the knowledge acquired in the frame of the Linux can be used in the NuttX without any difficulties. So, the second application. The main idea is that there is a growing need for food worldwide, and this need requires the development of high performances, high productivity, and sustainable agriculture, which implies the introduction of new technologies into each stage of the plant development. However, many elements affect crop development, like the one presented on this slide. But one of the most important is the existence or not of the different type of diseases. In this project, I developed an intelligent system to assess the healthiness of vines based on the characteristics resulting from the analysis of the vine leaves, such as texture, shape, or color. The intelligent system presented here is able to detect two different diseases. The first one is blister mite, which is generated by a mite species infecting grape leaves. This disease is also a vector for other viruses that affect vines. The treatment for these diseases should be applied when the first mites appear. If they are allowed to develop, they will do so quickly, mainly because this mite has between 5 to 7 generations in a year. The second detected disease is grapevine leaf roll. This disease is one of the most important grapevine viral diseases affecting wine grapes worldwide. The main problem with the grapevine leaf roll diseases is that there are no ways to cure an infected wine, and there is no chemical control for grapevine leaf roll disease. Therefore, the only solution is to remove and destroy virus-infected vines. So, as a direct conclusion, the field survives, and the detection of grapevine leaf roll diseases are the only valid approach used up to this moment. The grapevine leaf roll diseases is considered one of the most economically destructive grapevine virus diseases. There are many estimates of the economic cost worldwide. Some estimated loss ranges from $30,000 to $226,000 per hectare. In another estimate, the losses are between $25,000 and up to $40,000 per hectare. And in another approximation, the loss is up to 77% revenue decline. So, as a direct conclusion, this intelligent system is important because a timely diagnosis and accurate identification of grape leaf diseases are decisive for controlling the disease spread and ensuring the grape's healthy development. Moreover, the early detection of the diseases will determine the use of pesticide only when necessary, with a positive impact on the environment. The intelligent detection system is supported by IMX8M Plus development board, known under the name of NavQ+, carried over the entire vineyard by an NXP hover game drone, a drone that was presented before. The development board also has a neural processing unit on which the deep neural network is executed in real time. At the level of IMX8M+, the functionalities were implemented using the support of Robotic Operating System version 2. Additionally, a 0MQ client application and a 0MQ server were used for debugging the development application in real time. The system incorporates a depth sensor to guide the drone through the rows of vine. For vine planted industrially with mechanized soil maintenance, there is a distance between rows between 2.2 up to 2.5 meters. So we have plenty of space to fly. The Google Coral camera was used for plant anomaly detection. Of course, the depth sensor also has an RGB camera that could be used instead of the Google Coral camera. Still, initially, the functionalities were implemented by using both cameras to ensure that the data stream could be received without any lags or other types of problems. Next, I included a leader light type sensor in the system because maintaining a constant altitude through the GPS and the barometer sensors is not very accurate. The components that implement the software part of UAV drone were developed as a single Robotic Operating System 2 package having 4 nodes. All the communication and synchronization between nodes were done through topics. The detection system is based on TensorFlow Lite model and runs on the health plant node. The detection system starts when the UAV drone is set in off-board mode. The node takes note of this fact from the flight control node through the flight off-board topic. And in this mode, the detection process starts. The health plant node publishes 2 topics related to the detection process: detect vitis and detect leaf roll. These 2 topics post the area of lives for each class detected. This publication of affected leaf area can be used to create a real-time map of the extent of the crop damage. The flight control node is connected to PX4 autopilot, being able to control the UAV based on the velocity and position modes. It is also able to know the status of the drone at each moment. This node can arm, disarm, take off, land, etc. the drone accordingly with the necessity resulting from the off-board control. Each of the following nodes, video publisher node, flight control node, and health plant node, has a specific topic for publishing images required for debugging purposes. The video broadcast node can subscribe to a specific image topic and stream the images to 0MQ video server through, of course, 0MQ streaming protocol based on the Wi-Fi link. Mainly because in this project I want to detect only 2 types of leaves, and because these leaves do not belong to the categories on which classical deep learning networks were trained, like person, car, airplane, bus, train, boat, bird, cat, dog, and so on, I used the transfer learning paradigm. So I used the MobileNet version 3 deep neural network, which is widely used for image detection and recognition. This neural network already has trained layers that can identify different features, like outlines, curves, edge, etc. Training these layers required a lot of training data and also required a lot of training time. But using all of this already embedded knowledge, I only retained the last layer, which was replaced with a new one, with outputs for detecting elements probabilities and outputs pointing to a specific area in the input frame. So in order to train the last layer, a new training database with images for the two classes was created. 80% of the images from the database were used for training and 20% for testing. 4. The image annotation, model selecting accordingly to the desired accuracy, model training, model optimization for efficient neural processing unit execution, and model validation. I used IAQ environment that is presented in this slide. Following the training process, the detection performances was a little bit more than 86%. Okay, but keep in mind, this project was a proof of concept. Thus, I was able to prove the functionality of this approach. And, of course, it can be applied in the same way to assess the health of fruit, tree, maize, rice, or any other plant based on the state of the leaves. Right now, I'm working to increase the classification performances. From the point of view of NuttX operating system, I had less interaction with this operating system in this particular project. My application was developed entirely on the companion computer and communicated with the PX4 autopilot through micro RTPS bridge, micro real-time publish and subscribe bridge. For example, I interacted with the NuttX operating system when I built the autopilot. Here you can see the menu config tool. Of course, here is a graphical user interface variant that was used to modify the PX4 board configuration, adding, removing modules, drivers, and other features like NuttX components. In addition, the client component of the micro RTPS bridge was executed at the boot time of the flight management unit based on the NuttX operating system features. Moreover, I extensively use the NuttX integrated shell interpreter to launch different component drivers or to check the state of the system, like CPU and memory usage, to check the state of the GPS or to test the motors, scan for I2C devices or to list topics, to list the content of the topics, to check the state of a Mavlink connection or to erase the flash memory. In conclusion, the NuttX operating system is an essential component of any PX4 UAV, in my case of the Hover Games drone produced by NXP company. And, most importantly, the deep understanding of this operating system will help you build a UAV system that is as safe, effective and reliable as possible. Thank you very much.